Welcome back, Physics 11, to another exciting episode of Mr. Wellsby Gives Notes. So today we're going to be talking about using vectors and scalars. These are terms you're probably familiar with, but just as a quick recap, remember that scalars, they do have a magnitude. So they have a size or a magnitude, they'll have a number associated with it, but they will not have a direction. So no direction with a scalar. Vectors, they also have a magnitude, so we would associate it with a number, but they do have a direction as well. So vector gives you how large the quantity is in terms of a number, but it also tells you which direction that quantity is being affected or is happening or is extended in some way. So some examples of that would be, let's go with forces. So when you're applying a force, you have to obviously apply a force in a direction. You push someone to the left or to the right. Another one that we have is displacement and velocity. I mean, there's lots more than these, but these are just three examples. If we're looking at scalars, some of those might be time. Time is a scalar. We just say it's 2 minutes. We don't say it's 2 minutes upwards or 2 minutes backwards or 2 minutes to the left or right. Another one is distance, being a scalar, and speed. So these two here, displacement and distance, these are closely related. So if I was standing in front of a student, for example, I could give the distance and say the student and I are 2 meters apart. Remember, social distancing. If I wanted to discuss it in terms of displacement, I would say that student is 2 meters in front of me, or 2 meters to my left or to my right. So displacement would include the direction. Distance would just be the number, 2 meters apart, etc. Velocity and speed are also closely related. That's not a very attractive star. So velocity and speed are also closely related. Again, the difference just being that the velocity includes direction. So for example, if we're talking about speed, this is what your car would give you on your speedometer. When you look at your car when you're driving, it says you're driving 100 kilometers an hour. But if you were looking at your GPS, then your GPS would tell you, yeah, you're going 100 kilometers an hour to the north, or you're going 100 kilometers an hour to the west, for example. So that's the difference between velocity and speed. Now, on the right, we have a huge list of these quantities. So I'd like you to pause the video and make your best estimations or best guesses on whether you think these quantities on our right are going to be vectors or scalars. So you can pause the video now and we'll come back to it in a moment. Okay, so if you have paused it and you've tried your best, let's see how well you did. So I'm just going to write S for scalar and V for vector for all these quantities. So density is a scalar, displacement vector, scalar, scalar, scalar. Energy is a scalar, that may surprise you. It doesn't have a direction. Field strength, so we're talking about gravitational field, for example, that does have a direction. Gravity is definitely pulling us downwards when we're on the surface of the Earth. It's not just pulling us in no directional. So we need the direction there for field strength. Likewise, force. So we're having a force of gravity pointing downwards. Friction is, of course, a type of force, as is weight. And so any force will be a vector quantity. So weight, friction, etc. Mass is a scalar, momentum is a vector. This is our tendency to keep moving in a given direction. So what makes it difficult to slow down a moving car, for example. Power, which is related to energy, it's just the rate of energy transfer. This is also going to be a scalar, just like energy is. Speed's a scalar, it's not giving us a direction. Scalar, vector, scalar, and work done is just another way of saying energy is being transferred, just like energy. It's also a scalar. So see how you did. Hopefully you got most of those right. Now, as I've already mentioned before, velocity is a vector quantity. It has speed in a certain direction. And so when we calculate velocity, we need to know what the displacement is. So the displacement is symbolized by the symbol S, and this is also a vector. So S is one that we normally use. Some people will write it as D as well. but also when we're writing a vector, a common notation, if we really want to be clear about what we're talking about, is this notation right here. So I've drawn a little arrow on top of the D. So what this is saying is that this is displacement as opposed to distance. So drawing that little arrow, this is a vector arrow. So it's telling us that this is a vector quantity that we're talking about. So when we're talking about acceleration, here's another one that didn't come up in the list before. But acceleration is the change in velocity. And if we really want to be a bit more specific, we want to be a bit more accurate, acceleration is really the rate of change velocity. So how quickly we're speeding up, how quickly we're slowing down, or because it's a vector, how quickly we're changing direction. The formula that we have for that is written this way. So A, and I've drawn the A with this arrow to indicate it's a vector, is equal to delta V, and that's divided by t. Now v is also a vector, so I've drawn the arrow, but t is a scalar, so there's no arrow. Now triangle, what is that triangle? So triangle is the symbol delta. So this is the Greek letter delta. This is the capital letter delta, not the lowercase one, of course. And this means change in. So delta V means change in V, or change in velocity. And this is always going to be your final value minus your initial value. So delta is just final V minus initial V. So delta V would be V final, your last speed, minus your your final velocity minus your initial velocity. If we were referring up here to velocity, we could say velocity is the change in displacement divided by time. So the final position minus the initial position divided by time. So let's look at an example. This is kind of a weird example for you. If you have an object moving in a circle at a constant speed, so let's say you attach a weight to the end of a string and you swing that around your head, is that object accelerating? And the answer may surprise you, because even though the speed is the same, the direction is constantly changing. And so if we know acceleration is a vector, and we know it's just the change in velocity divided by time, there is a change in velocity because there is a change in direction. So this is kind of a surprising one for a lot of students when they first see this. So let me just draw this out for you so make sure it's clear what I'm referring to. So let's say this is a path of an object, and at this point here, this is just some object I'm holding on a string. At this point here, the object's moving to the right, and a short amount of time later, it's going to be moving downwards. So even though this and this are the same size, the magnitude has not changed, the speed is the same, the direction has changed. Anytime we are changing v, which we did, we definitely changed v, it was say 2 meters to the right and now it's 2 meters downwards, those are different velocities. And so because the velocity is different, it has accelerated. So kind of a weird one that's a bit unexpected. Now, just so you know what the conventions are, and by convention I just mean a standard that's widely accepted across the scientific community when we're referring to vectors that are as follows. So vectors that are east, north, up, to the right, all of these we consider to be positive vectors just by standard kind of way of dealing with these, we always consider these to be positive, and any vectors that are west, south, down, or to the left, we would of course consider these to be negative vectors. So the reason why is that we need to keep track of what directions things are going, because sometimes they will act in opposite directions. So an example of that would be if I'm standing here and I have one student pulling me with 5 newtons to the right, and I've got another student pulling me 4 newtons to the left. Well, if we just add these together, you would think that I'm being pulled with 9 newtons. But hopefully you can see here what the overall force on me would be. We would have 5 newtons to the right, so we would call those positive, and then we're going to add 4 newtons to the left. But remember, when we're adding left newtons, we would call these negative. So we would say we're going to add negative 4 newtons, or we could just, of course, simplify that and say we're subtracting 4 newtons. So I have plus 5 minus 4, and this is going to equal 1 newton to the right. That's going to be the overall force. And because I kept this idea of positives being to the right and forces to the left being negative, this takes care of all my math for me. Okay, hopefully that's okay. So we've done an example where there are two forces that are in the same, they're parallel to each other. So one to the right, one to the left. Well, what happens if I add vectors where they're not in the opposite direction or the same direction? So let's take a look at this example here. I'm going to take direction into account. Sorry, this is a typo. That should be 90 degrees. So let's say I draw this diagram out here. This is going to show someone walking 3 meters from A to B. So this is A, and this is B, and I'm walking 3 meters in this direction. And then I'm going to turn right through 90 degrees, and then I'm going to walk to C 2 meters. So this is point C. So I've gone from A to B to C all in one trip, and we can see that the total distance that I've traveled, total distance, not displacement, the total distance will be 5 meters. I walked 3 meters, and then I walked 2 meters. So total distance as a scalar is going to equal 3 plus 2. And this is something that's important to note. When adding scalars, we're just using traditional math that you've been doing since, I don't know when you learn addition, kindergarten, grade 1, whatever it is. So when you're adding scalars, 1 plus 1 equals 2. There's no arguing with that. Whenever you're adding scalars, if you have, let's say, $1 plus $1, you're going to have $2. Because a dollar, for example, would be a scalar. It doesn't have a direction. So this is always going to be true when you're adding scalars. 1 plus 1 equals 2 as an example. Now in this case here, what if I want to know my displacement? So my displacement is the change in position. And what I mean by change in position, we use this delta S, change in position is the final position, so S final, minus my initial position. Okay, actually, let's just make it easier for you. We'll just do, yeah, that's fine. We'll keep it as S. So final position minus initial position. So this is the difference from point C to point A. So my displacement is this line right here. Now, if I look at this triangle, I know I've gone 3 meters, we'll call it north, and then 2 meters to the east. I know my distance is 5 meters, but what is my displacement, and how would I calculate it? So if you feel confident that you can try and answer this question, this should look like some pretty familiar trigonometry that you may have done in previous years. Please feel free to pause the video now and try and solve this. And what we're going to try and solve ultimately, we know we need to have a magnitude and a direction. So what is the magnitude of my displacement? What's the magnitude of the difference in position from point A to point C? So how far I've actually traveled in terms of the difference between where I ended up and where I started. In other words, what is this distance here? And because I'm talking about displacement and it's a vector, I also need to consider the direction. So what is this angle here that's going to help me find out my total displacement? So what I'm trying to ask essentially is from A, how far did I move and in what direction did I move, end up at C? And I'll give you a hint, it's not going to be 5. Hopefully you can see it's going to be less than that. So pause the video here if you think you can give it a try and go for it. Okay, hopefully you have given it a shot. So if you're feeling confident, hopefully you've got some of the information at least finished. So the first thing we're going to do is we are going to need to try and calculate the distance here. Now, if we're trying to find the distance of a triangle, we can see that this is 90 degrees. And so hopefully Pythagorean theorem popped into your mind. We know the Pythagorean theorem tells us a squared plus b squared equals c squared, where c is the hypotenuse. So in this case here, this is going to be our a, this is going to be our b, and this is going to be our c. So this is telling us here that 3 squared plus 2 squared equals c squared. And this is going to be 9 plus 4 equals c squared. And so c is going to be the square root of 13. And this is approximately, let's see, square root of 13 is approximately 3.6. Okay, so you can put that in your calculator. You'll get roughly 3.6, approximately equal to that. Now, what about if I'm trying to find the angle? So in this case here, if I'm looking at my triangle, from this angle, this 2-meter line is going to be the opposite, and this 3-meter line is going to be the adjacent. So which of our three quantities, which are our three trig quantities, sine, cos, or tan, has opposite over adjacent? Well, hopefully you remember that it's tan. So tan of theta is equal to the opposite over the adjacent. This is equal to 2 over 3. And then what you plug in your calculator is, or theta equals the inverse tan of 2/3. And again, this is approximately 34 degrees east of north. So my total answer for this question is going to be 3.6 meters, and that's going to be 34 degrees east of north. That's my displacement. From A to C, I've moved a total of 3.6 meters, and I moved approximately 34 degrees east of north. And what I mean by east of north is that I start kind of a line that goes north, and I figure out how far to the east I had to travel from my north line. So I went to the right, or I went clockwise, 34 degrees away from north, so east of north. Okay, so AB and BC are vectors, and they're shown by a single arrowhead on the vector diagram here. AC is what's called the resultant. You could call it the overall vector, or you could call it the total vector. So resultant is probably the most common, but you can also refer to it as the overall vector or the total vector. And sometimes this is shown by a double arrowhead. I'm more of a fan of using a dashed line. So for me, a dashed line tells me this is the resultant vector A to C. So to combine any two vectors, we can draw a triangle like we had up here, ABC, where the lengths of the side represent the magnitude of a vector, for example, 30 and 20. And the third side of the triangle, that dashed line, shows us the magnitude and direction of the overall, or of the resultant force, the resultant displacement, the resultant velocity, etc. Now, if we were to draw a diagram carefully, so let's say, for example, we took a ruler out and we took our protractor out and we drew exactly a 3-centimeter line, we'll call it a 3-centimeter line, or I have a big meter stick and I draw a 3-meter line. And then if I draw another arrow that's 4 meters long, and I'm very, very careful to draw this exactly to scale, well then I would be able to calculate this without even using a calculator. I could just measure this directly. So if we measure something to scale, 3 meters, 4 meters, 5 meters, would be like we can use a carefully done drawing to actually determine what our third vector would be. But of course, that's not a very practical means of doing it, and so calculation is the way that we're going to do it, but in theory, we definitely could. And it's also important to note that if we draw the vectors in the opposite order, they're still going to give us the same answer. So let's say, for example, I've just drawn this up here. So I had 3 and 4, and this gave me 5. So I had 3 plus 4 equals 5. But hopefully you can see if I did 4 plus 3, I'm going to get the same answer here. So here I went 3 meters plus 4 meters. Here I went 4 meters plus 3 meters. Either way, my answer is going to be the same. So when you're adding vectors, so adding the vectors, order doesn't matter. Okay, and so just a couple quick reminders about solving these. Now we're talking about right triangle. So in general, we're talking about right triangles here in this lesson, but we know that all of the internal angles of a triangle add up to 180 degrees. And so if we have a right triangle, which is 90 degrees, obviously the other two add up to 90. So if one is 30, then the other one's going to be 60. We can determine that. And we also have Pythagorean theorem. Again, just a reminder, we talked about this above, where a squared plus b squared equals c squared on a triangle like this. And also on a triangle like this, sine is going to be opposite over hypotenuse, which in this case is going to be b divided by c. Cos is going to be adjacent over hypotenuse, which would be a over c. And tan is going to be opposite over adjacent, which in this case would be b over a. So those are our three Pythagorean relationships, or sorry, three trigonometric relationships and our Pythagorean theorem. And that's pretty much all you need to know in terms of answering these types of questions here. So that's it for this short video. Please try the questions, and as always, email me if you have any struggles along the way. Thank you.